Okay, so uh, let me start. So welcome to the week two of the problem solving session of Introduction to Atmosphere and Space Science. So this is the second week, and altogether we will be discussing about the composition of the atmospheric air, then the mass of dry air and the mass of the vapors, which we will see, and then the specific gas constant, about the surface pressure, then hydrostatic equation, then vertical variation of pressure in different atmospheres. Again, it is for the second thing, that is another atmosphere. I will let you know. Then the lapse rate, tropopause height, why it varies from equator to the poles. Next is ozone. I will give some insight over the ozone, although I have given certain things about the ozone in the week one. Next is the time scales and the spatial scales of the atmospheric phenomena. And then the atmospheric window, then atmospheric variables conventions, which are very important, and the pressure gradient force, the gravity, and some assignment questions which will be there, and some questions which I have framed which will help you to solve these equations, uh, and that's all. Okay, so now I can turn my camera off and let's start the recording. Just a minute. Let me see whether the recording is started or not. Yes. Okay. So as you can see the screen, the first thing which is written here is the composition of the atmospheric air. And so initially you can see that these are the gases which are present in the atmosphere. Its percentage contribution is shown here, and the molar masses of those gases are written here. Now, you cannot find the water vapor over these region, over these gases which are present, which are listed here. So you cannot find out the water vapor. So what happens is that using these things we will calculate the mass of the dry air and the mass of the vapor. So atmospheric air. So excuse me, just a minute. Yes. So the atmospheric air, let me write it. Atmospheric air has two things. One is the dry air, another is the vapor. So what is the dry air except this vapor? Just a minute. Okay, let me start again from this. So this is the mass. So what I have said is that the atmospheric air are two kinds. One is the dry air, another is the vapors. So what are these vapors? These are nothing but the water vapor. And we know that the mass of the, since we are calculating the mass of the dry air and the mass of the vapor, so mass of the vapor is same as that of the H2O molecule. That is, we are talking about the molar mass here. So this is 18 grams per mole. But the mass of the dry air should be calculated using these all gases and its percentage contribution and molar masses. So how to calculate the mass of the dry air? So let us see. So let us consider this mass of the dry air as md, and this is nothing but mv, the mass of the vapor. So what is the mass of the dry air? The mass of the dry air is written as summation of the molecular weight, or what do you mean by molecular weight? The molar masses of each individual gases which are listed here. So these all molecular weights times the percentage contribution of each gas, divided by summation of the percentage contribution of each gas. Then only we will get the dry air's mass, or what you call as the dry air's molar mass. Okay, so the summation is in I, so you can understand. So how we can write? So it will be like md is equal, see, this is first gas is nitrogen, so this 78.084 times 28.013 plus 20.984 plus 31.998, and you can see from this particular percentage contribution thing that the total summation of this percentage contribution will be nothing but 100%. It's quite near to that of the 100%. Therefore, in the denominator we can write it as 100. Now in the numerator, how we will write? We will write it as, so let me write it. It is 78.084 into 28.013. So this is the percentage contribution, this is the molar mass of nitrogen, plus then what the oxygen comes, that is 20.948 into 31.998, and you continue adding all those things so on, and divided by 100, which is the total percentage of contribution. Okay, so now what will be the md? Therefore, if you calculate all these things, this md, the mass of the dry air, or what you call as the molar mass of the dry air, comes out to be 28.96 grams per mole. Well, this is of course because if you see here, the maximum percentage of contribution is nitrogen, and whose molar mass is 28.013. It is obvious that it will be the molar mass of the dry air should be nearly to the molar mass of the nitrogen. Why? Because it is capturing maximum amount of percentage contribution in this atmospheric air of nitrogen is maximum 78.084. So it should be closer to 28, and we have got the value to be 28.96. So 28.96 is the mass of the dry air, and the mass of the vapor mv is 18 grams per mole, which is nothing but the mass of the water vapor. So atmospheric, from this slide or from these two slides, we have seen that what are the components of, what are the gases which are present in the atmosphere, its percentage contribution and molar masses are listed. From that we have calculated the mass of the dry air using this kind of a formulation, and we have seen that the atmospheric air consists of two things. One is the dry air, another is the vapors. Vapors are nothing but the water vapor, and water vapor's molecular mass is, or molar mass is, about 18 grams per mole. Whereas the mass of the dry air as the percentage contribution of nitrogen, which is the maximum, is having a molar mass of 28.013. It is expected that it should be near 28 grams per mole, and we have seen that if you calculate using this particular formula of md, you come at a value of mass of the, or the molar mass of dry air, to be 28.96. So this is the thing which I want to show you first. Second thing is the specific gas constant. Well, for understanding the specific gas constant, we have to go to the ideal gas equation. What is the ideal gas equation? PV is equal to nR star T. We all know, we are all familiar with this ideal gas equation. So PV is equal to nR star T, where N is the number of moles. N is the number of moles. Now N, the number of moles, can be written as what? Number of moles can be written as given mass by molar mass. Okay, so the number of moles can be written as given mass by molar mass. So we can write it as small m by capital M, where small m is the given mass of a particular gas, and capital M is the molar mass of that particular gas. Now what is this R star represents? This R star, we all know, that is the universal gas constant. So this is the universal gas constant, and this T is the temperature of the gas, and P and V, we all know, these are the pressure and the volumes. Okay, so now So what is the value of this R star? Since it is a universal gas constant, it should be having a constant value. So what is that value? That value is 8.314 joules per Kelvin per mole. Remember this thing, it is per mole. Joules per Kelvin per mole is the your universal gas constant. But what we are talking about here is the specific gas constant, something different. So what is this specific? We have heard about the term specific heat capacity, specific volume. What is that specific means? This word always means that specific. That word specific always means per unit mass. It can be per unit molar mass as well as per unit given mass. Anything. It is actually representing per unit mass. Specific word means per unit mass. In thermodynamics, this word means per unit mass. Okay. So specific gas constant. Of course, this R star should be divided by some mass. So let's see how we are going to get this particular thing. Okay. So let's again write the ideal gas equation. Again, PV is equal to N R star into T. Right. So what I do is that now PV is equal to given mass by molar mass into R star into T. Right. Now what I do is that this P V by small m, I took it in this side, and we have R star by M by T. Okay. Now in another way we can write this particular thing. See, this is PV is equal to M R star by capital M into T. Now P is equal to M by V into R star by M divided by T. Both are correct. This is also correct. This is also correct. But can be represented by different ways. See, this is what volume per unit mass, and what I have said that per unit mass means specific. So what we will call this particular term is P alpha is equal to R star by M into T. So this is the molar mass. What is this alpha then? Therefore, because it is volume per unit mass, we call it as this alpha as the specific volume. This alpha is known as the specific volume, whereas this M by V, which we call as the density, M by V is called as the density. So we all know about this formulation of density. So what we can derive from there, so the density can be represented as rho. So rho is equal to 1 by alpha. Okay. So density is 1 by specific volume. One thing we have seen. Another thing which is important in these expressions, if you write this R star by M is also divided by mass. This R star by M, which is that universal gas constant R star divided by the molar mass of the gas, that can be represented, that can be called as, since it is per unit mass again, so it is called as the specific gas constant. This is what I was talking about, specific gas constant. Okay. So this is the specific gas constant. Now what happens is that now for this, see, this is R, which can be represented by R. This is R actually. So what we can do is that I am writing it here now. So this R is equal to R star by M, isn't it? Now for dry air in the atmosphere, if we consider atmosphere only, focus on atmosphere. So this dry air, MD is how much? 28.96 grams per mole. So RD, that is specific gas constant for dry air, is nothing but 8.314 joules per Kelvin per mole, which I have already written, divided by 28.96 grams per mole, isn't it? So you can take out mole and mole. Now you have to convert it into the SI unit, so gram should be converted into kgs. For that, what I have to do, I have to multiply the numerator with 1000. So 8.314 into 1000 divided by 28.96. So now it can be written as joules per Kelvin per kg. Now see, this is per unit mass coming. So this will be nothing but 8314 divided by 28.96. And if you solve it, it comes out to be 287 joules per Kelvin per kg. So remember this RD, this for dry air, specific gas constant is 287 joules per Kelvin per kg. Now for vapor, exactly similar, you have RV, therefore that will be equal to what? 8.314 into 1000 divided by mv, that is nothing but 18 grams per mole, and that comes out to be nearly 461.5 joules per Kelvin per kg. So remember these two values, that is for R, in case of atmosphere, RD is 287 joules per Kelvin per kg and RV is 461.5 joules per Kelvin per kg. So these two values needs to be remembered. These two values are extremely important in when we are talking about the thermodynamics of the gas. In the atmospheric thermodynamics, these RD and RV are widely used. Another thing will come, that is after that moisture, the moist air, for the moist air thermodynamics, another thing will come, that is the specific gas constant for the moist air. That we will see when we will be talking about this moist air thermodynamics. Okay, so this is what is the conclusion of from this slide, that ideal gas equation, which is represented in terms of moles, number of moles, R star and T, this can be further written as in terms of specific volume, or also it can be written in terms of the density rho. I will use this particular thing in this lecture only for a particular derivation, and from this only this specific gas constant thing arises. And for dry air we have calculated the specific gas constant to be 287, and for the vapors it comes out to be 461.5. That is the conclusion of this particular slide. Okay. Next is surface pressure. Well, what the arrangement is shown here is like a barometer, and it just, we all know that it's a mercury thing, it rises over this particular region, and this here the pressure is 0, just above the fluid the pressure is 0, and this is the P atmospheric pressure. So the P here horizontally the pressure should be same, so P should be equal to PA. And what is this P? P can be written as 0 plus the density of the fluid into G into H, and the height of the fluid occupies, and that P is equal to PA. So the atmospheric pressure can be calculated using the rho G into H, where experiments says that using mercury, H rises to 0.76 meter, 76 centimeter, G is known 9.81 meter per second square, and this density of mercury is about 13600 kg per meter cube. So if you calculate my PA, the atmospheric pressure, comes out to be 1013.00 pascals. This is the the atmospheric pressure. Now surface pressure may sometimes equal to the atmospheric pressure, but sometimes may not be equal to atmospheric pressure. Why? Because somewhere there is some oceanic depression is present, somewhere there is mountains present. So mountains, this surface of the mountains is nothing but the surface pressure, or the pressure over this surface of the mountain will always be the surface pressure. But since it is above the surface, actual mean sea level, above the mean sea level, so what happens is that here the pressure decreases. So why should the pressure decrease? The pressure should decrease because you have a column of air. Suppose you have a column of air. This is the surface and this is the top of the atmosphere. So I am writing this is the top, this is the surface. Okay. So now what happens is that whatever pressure is experienced at the surface is actually because of all the gases which are present here. All the gases which are present here, because of this particular surface is getting some pressure. Now if you go at a particular height, say this, so here we are trying to find out what will be the pressure over this particular region. So what will happen? It will get the pressure, it will measure the pressure that is just above this particular region, and so the gas here is less as compared to the gas when we are measuring from the surface. So the pressure here will be less as compared to the pressure here at the surface. Okay, so surface pressure may vary from place to place, where mountains are there, where rivers are there, and some different land masses are there. The pressures are different, the surface pressures are different, but we assume that the surface pressure is nothing but the atmospheric pressure, and that is equal to 1013 hectopascals, because 1013 pascals means 1013 hectopascals, and or we take it as, for numerical calculation, we take it as 1000 hectopascals. Two units of surface pressure which is widely used, or pressure in the atmosphere is widely used, is one is the hectopascals, another is the millibar. And actually the relation between hectopascals and millibar are same. 1 hectopascal is equal to 1 millibar. So we generally take this surface pressure, or the pressure at the surface pressure, to be 1000 hectopascals. Okay, instead of 1013 we take it as 1000 hectopascals. But if you take 1013 hectopascals, the answer will come, the numerical will be solved properly. Fine, this is the concept of the surface pressure, which is nothing but the atmospheric pressure. But as I have already told, surface pressure changes from place to place, and as a result you can find out that this surface pressure will change, because somewhere there are mountains, somewhere there are oceanic depressions, and because of which everything will change. Fine. Next is the hydrostatic equation. Now why am I coming to the hydrostatic equation, although in the week 3 it is being covered? So why am I coming to the hydrostatic equation is to derive what we have seen in the week 2. It is that the pressure which varies with altitude. So this pressure which varies with altitude is Pz is equal to P naught e to the power minus Z by H. This kind of formula you have seen, and you might be using it in the assignment 3. So I want to derive this formula. Actually this formula comes at a particular approximation that I will show you. But first, what is a hydrostatic equation? Well, this hydrostatic equation I will derive with a very general kind of approach. Well, so starting with, I will draw a small cube kind of. Okay, so this is a, you can say that is a air parcel, some volume of air is there, whose density is rho. Okay, whose density is rho, and here at this height and this height, at the above height the level is Z plus delta Z, and the below height is Z, and it is from a reference, say Z is equal to 0. This height is Z and the above height is Z plus delta Z. The area, this area, that is dA, is actually 1 unit square. Let us consider this dA to be 1 unit square. Fine. Now, so here the pressure is P of Z, here the pressure is P of Z plus delta Z. Now, as I have mentioned earlier, that P of Z plus delta Z will be, of course, be less than P of Z, isn't it? Because less gas is putting pressure at a higher altitude. So that's why P of Z plus delta Z will be less than P of Z. Great. Another thing which is acting over this particular air parcel is the mass of, or the gravitational acceleration, that is mg. The force mg will be acting over this particular region. Now what we will do is that so how to start this particular thing is that the pressure force which is acting over this particular body, so let's write the pressure force which is acting in that particular body. Okay, so this will be what? P of Z plus delta Z, or let us write, so P of Z minus P of Z plus delta Z. Why am I writing? Because P of Z is higher pressure to that of the lower pressure. So total pressure is this Pz minus P of Z plus delta Z into dA. That will be the force. But dA is unity, that I will manage. So that will be equal to mass into gravity, and mass is what? Rho into dA into delta Z. That is density into volume is mass. So into G. That is the equation. Okay, fine. Now dA will of course get cut out. So what I am having is this Pz minus P of Z plus delta Z. Okay, that will be equal to rho G dz. Now this Pz plus okay, so now what I will do is that I will take the minus out and I write it P of Z plus delta Z minus P of Z divided by delta Z or dz, whatever you want to write it. That will be equal to rho G. Fine. So you see, this is a very familiar expression. What is that? This is nothing but dp dz. Correct? At limit delta z tending to 0, you can find out this is equal to dp dz, and that is equal to rho into g. Therefore, we can write this dp is equal to minus rho g dz. This is actually the hydrostatic equation. And I will use this particular equation along with the ideal gas equation, which I have already showed to you, uh, to derive this particular expression of the pressure variation with height. Fine. So, okay, let's do it. See, vertical variations of pressure in different atmosphere. So the first atmosphere which I will talk about is the isothermal atmosphere. That is the isothermal atmosphere. As you see, the name suggesting isothermal means what? Temperature is constant. In the atmosphere, temperature is constant. Well, fine. Which is not a realistic case. Temperature is not constant. We have seen the atmospheric temperature variation with height. Temperature varies in a zigzag manner. So temperature first decreases in the troposphere, then it increases in the stratosphere like this, and then in the mesosphere it decreases, and again thermosphere it goes on. So it's a zigzag manner temperature curve. T is never constant in the atmosphere, but it is an approximation which we are taking to derive how the pressure will change with altitude. Well, now to start with, what we will do is that we will use these two approximations. First is your hydrostatic approximation I will use, and then I will use the ideal gas equation. Well, so let's start with the hydrostatic approximation. So dp dz is equal to minus rho times g, right? And and p is also equal to rho rt. Now what is this r here? This r here is the specific gas constant, not the universal gas constant, because I will write universal gas constant with r star. But I have already shown that when you are writing it in terms of density, the ideal gas equation in terms of density or in terms of specific volume, you have to write this r to be the r should be the specific gas constant. Fine. Now what I will do is that I will use this equation 1 and equation 2 to derive this particular expression which I have just showed about the pressure variation with height. Well, so start it with rho in the from equation 2. So from 2 we get rho is equal to P by R into T. Now here the T is constant, so it's fine to write this particular way. Okay. Now put this in 1. Sorry. Put this in 1. So what will happen? dp by dz will be equal to minus p by rt into g. Now dp by p will be equal to what? Minus g by rt, and put the dz here. Now you see, this is the integral which I have to solve to understand what will be the pressure variation with height. Okay, so now temperature is constant, r is a specific gas constant, so it is also constant. G is universal, the gravitational acceleration, that is also constant. So this particular term is entirely constant, so I can take this term outside the integral and solve it. And from where to where the limit persists? From the surface pressure P0 to P, and from 0 to some height z. Okay. Now this integration is easy, it's just log of P by P0, and that this will be minus G by RT, and dz integration will be z. Simple. Okay. So and we can write this as P is equal to therefore P0 e to the power minus G by RT into z. Or we can write P is equal to P0 e to the power minus z by h. Now what is this h? Where h is nothing but the scale height of the atmosphere. Scale height of the atmosphere So scale height of the atmosphere means what? It is it is that height it is that height at which P becomes equals to the surface pressure times E, P naught by E. E is this exponent 1, 2.78. So P will tend to P naught by E at whatever height, that will be equal to the scale height, and its value is, as you can see from this expression, if you compare these two, the value becomes RT by G is nothing but the scale height. You can check the units, it comes out to be in the meters, because this is meter per second square, this T is in Kelvin, this is joules per Kelvin per kg. If you do it, it comes out to be in meters. So we have derived this expression, and most of the this week 3 assignment can be done using this particular formulation. Okay, so this is one of the atmosphere with a only approximation that temperature is constant. Temperature will remain to be constant, and therefore we can write P is equal to P naught e to the power minus Z by H. Fine. Okay. Next is another vertical variation of pressure. This is something different from this. This is not covered in this particular course, but I am giving it for your interest, which is a more realistic kind of an atmospheric situation where temperature decreases linearly with height. We know that in the troposphere, okay, so in the troposphere, we know that temperature decreases linearly with height, and after that in the stratosphere it goes up. So it's a kind of this tropospheric temperature distribution we are doing it. So what I will do is that this is an atmosphere second, that is T temperature at any height is equal to T naught, the temperature at the surface, minus gamma Z. This gamma is the rate at which the temperature is decreasing with height. Rate at which temperature is decreasing, and this decreasing can be seen by a negative sign, just forward to that. So decreasing with height. Okay, and this gamma is also called as the lapse rate. This is the lapse rate. There are many lapse rates in thermodynamics, atmospheric thermodynamics. One is the dry adiabatic lapse rate. Let me write it here. Just note down it, dry adiabatic lapse rate. You can see for the dry atmospheric it is. So dry adiabatic lapse rate. Then you have moist adiabatic lapse rate. Moist adiabatic lapse rate. Then pseudo adiabatic lapse rate. So these are all there. So there are many lapse rates which are present. In fact, environmental lapse rate is also present. Environmental lapse rate. Okay. So there are many lapse rate. I will not discuss it right now. I will discuss whenever it is required in the course. Okay. So T is equal to T naught minus gamma Z. This is the temperature variation with height. So if this linear decrement of temperature with height is the actual atmosphere, then how the pressure will vary with height? This is our question. How the pressure will change with height if the temperature of the atmosphere is changing with height using this particular expression. Okay, so let's start with the same thing. We will use the same two equations. One is the hydrostatic equation, another is the ideal gas equation. Okay, so let's write the hydrostatic equation first. So dP will be equal, dP dz will be equal to minus rho g, and another equation is P is equal to rho RT. Fine. Now I will replace again rho with P by RT and put it in this equation, and we get dP is equal to minus P by RT into G into dz. Correct? So dP by P will be equal to minus G by R. These are only constant. Now T is not constant. T is a function of Z. So it is T naught minus gamma Z. This is the expression now. Now this integral is from P naught to P, from surface pressure to some pressure, and this is from 0 to Z. So this is from 0 to Z. some height. Okay, now what I will do is that this is very easy to solve. This is log p by p naught. But what about this? I will do some substitution method. So t naught minus gamma z. So dy will be what? Minus gamma dz. Okay, now okay, at z is equal to 0, y will be what? T naught. At z is equal to z, y will be what? Same, t naught minus gamma z. Okay, let's just substitute it and put it here. So it will be, this will be log p by p naught, and that will be equal to minus g by r, and this becomes what? This becomes dz. Dz can be written as dy upon minus gamma, isn't it? From this, dy upon minus gamma, and what is left behind is y. T naught minus gamma is y, and this will be from t naught to t naught minus gamma z. Correct? Now just write it. Log p by p naught will be equal to minus will be cancelled out, so it will be g by r gamma only, and this dy by y will be log y, and going from t naught to t naught minus gamma z. Again writing it down, log p by p naught will be equal to g by r gamma, and what I can write it here is t naught minus gamma z divided by t naught. Okay, fine. Now another thing, oh sorry, there is a log here. There is a log here. So another thing which we can write is that log p by p naught, this is also a kind of, we can write in the logarithm. So log is log of t naught minus gamma z by t naught. Just in the power we can write this particular expression. Okay. Now log from both sides can be now cancelled, not cancelled, but you take the exponential both side, then you can chop out this log. So what I will get, the expression here is this: p by p naught will be equal to t naught minus gamma z by t naught, t naught minus gamma z by t naught to the power g by r gamma. This is the expression we are getting. So earlier, in the earlier case where there is an isothermal atmosphere, we have seen that temperature, this pressure, temperature is constant in that atmosphere, the pressure is decreasing with altitude in an exponential manner. But here in this case we are seeing it that the pressure is decreasing with altitude only, but in some power format. And we will see some numericals based on that, and you can apply the previous thing. This is not to be applied, I think, because this is not being taught to you in these NPTEL week lectures. So don't apply this particular formula, because this gamma will not be given. So don't apply this particular formula. Use this particular formula, that is p is equal to p naught e to the power minus z by h, where h is RT by g. Use this formula to solve most of the assignment questions. I have seen that it is mostly solved using this particular expression, and we will see one of the numericals in the later part, which I have framed, and we can discuss that particular thing. Okay, the immediate next thing is about the lapse rate. So that will be the lapse rate of the atmosphere. So I have already mentioned what is lapse rate. Lapse rate is, again we can write, it's nothing problematic, that is, it is nothing but the rate of decrement of temperature with height. Rate of decrement of temperature with height. So that is represented by gamma, that is minus dt dz. Okay, fine. Now now what happens is that this is now the tropopause height. So we have seen already in the previous lecture that tropopause is nothing but a region which is an equilibrium, which is a pause, which is an equilibrium between a troposphere, and this is a pause, and there is a stratosphere. In the stratosphere, ozone is there, which because of which some warming takes place over this stratospheric region. But in the troposphere, most of the atmospheric phenomena takes place where temperature decreases with height, and you can see that the most of the moisture is there in the troposphere region, and dry airs are present in the stratosphere region. So this is an equilibrium between the dry and the moist air, the dry stratospheric air and the moist or wet tropospheric air, and that is known as a tropopause. The question is why this tropopause height at the equator is very high and at poles it becomes very small. The reason for this is that in this equatorial region actually this most of the winds generally converges, and these winds converges from all the sides, and as a result of which what happens is that strong convective activity takes place, and because of which you can find out that the upward motion is vertical upward motion is very strong of the winds, and as a result of which this tropopause height is lifted upward. But as you go towards the poles, this kind of mechanism becomes very what you call as weak as compared to this particular thing over the tropics. But most of the times when you go towards the poles, that's why the tropopause height decreases. Of course, because of the temperature is one of the reason. Because of the temperature increase over this equatorial or the tropical region, because of the temperature increase, there is a chance that there is a low pressure region over these areas, and because of which the strong vertical ascent can take place. Vertical ascent of the winds I'm talking about. So these winds results into this tropopause height to increase. Now why there is a convergence? It can be explained using a general circulation model, but I will give you some insight of this. So what happens is that this is the earth, this is the equator, this is the subtropical high pressure belt, this is the subpolar low pressure belt. Okay, again this is the subtropical high pressure belt in the southern hemisphere, and this is the this is the subpolar low pressure belt. So this is about 66.5 degrees north, this is 35 degrees north, this is 0 degrees equator, this is 35 degrees south, and this is 66.5 degrees south. Okay, so what happens is that in the poles this is high pressure region, in both the poles this is high pressure region, this is a low pressure region, this is again high pressure region, and this is again equatorial low pressure region, again high, again low, and in this way it is done. Now how we have found out, because it's a long-term climatology of the winds, we have seen, if you can see using the model data or atmospheric model data, or you can see some observational data for long time period, if you average the winds, the horizontal winds as well as the vertical winds, you can find out that these regions or surface pressure, if you just average it out for a long period of time, then you can get these kinds of phenomena, and which is called as the general circulation. Because of this high to low, we all know that from the winds blows from high pressure to the low pressure. Of course, in the rotating frame like earth, Coriolis force will also act, and as a result some wind's direction will somewhat change. But I am not talking about the Coriolis force right now. Let us consider that I am not considering the Coriolis force, but the wind direction will be from high to low. Okay, and this will be also from high to low. So you can see that the winds are converging, the surface winds are converging over this region. So converging, if the surface winds tends to converge, it cannot penetrate the ground, so it should go upward. So there will be vertical ascent of the winds. Okay, now here in the 35 degrees north, again this is high to low, so there is a divergence of winds. You can see here again there is a convergence of wind, again there is a divergence, and again there is a convergence over this region. But this 60 to 60 and 66 and half, 60 to 66 and half degrees north and south, the convergence is weaker as compared to that of the equator. This equatorial low pressure belt is much stronger. This is much stronger, and that's why this vertical ascent is also very strong. Most of the convective activity takes place over this region, and as a result of which the tropopause height increases as compared to any other regions, or it falls towards the poles. So this is one thing which I wanted to show. And okay, so lapse rate I have already shown, tropopause height also I have shown, and next is ozone. Okay, so in the previous lecture I've written several equations about this ozone, and now also I will discuss some particular thing about the ozone, because it is important and it is curious to know about this ozone thing. It is important for the atmospheric as well as the climate of the earth. So as you know that this ozone, its molecular formula is O3, and it is measured in Dobson unit. Ozone is measured in Dobson unit. Okay, so what is this Dobson unit? Says that one Dobson unit is 1/100th of the millimeter of ozone in a particular column, in a column of air. Okay, so it is in 1/100th of the millimeter of that is ozone in the at HTP, definitely at the standard temperature and pressure condition. Fine. So now how this ozone is produced and how these ozones are destroyed. These are the two things which we will be talking about. First is the production. Let us consider first the production. How this ozone is produced. Of course, this ozone is produced from the oxygen. So the reaction, let me write and then tell you. So O2 plus H nu, the ultraviolet radiation, will give nascent oxygen or free oxygen. Now what happens is that one of the oxygen molecule with the nascent oxygen plus a is particular molecule is required that will take up the extra heat and extra energy, so that the energy balance is there. The conservation must be, the heat conservation or the energy conservation should be satisfied. Because of that, this extra mass is coming, and that will be equal to O3 plus A. Okay, this is how the ozone is created, and for this production of ozone, the wavelength of the ultraviolet which is required is less than 0.242 micrometer. Less than, so lesser wavelength, lesser ultraviolet wavelength is important for the production of the ozone. Fine, but more the longer the wavelengths in the ultraviolet region only, that will destroy the ozone. That will destruction of ozone. So how the ozone is destroyed? Let me see. So this is O3 plus, again the ultraviolet radiation only, that is destroying the ozone. So O3 plus H nu will give you O2 plus free oxygen. Now sorry, O3 plus O, this free oxygen, will give you 2O2. This is how the ozone is again converted into oxygen. So this creation and production is taking place based on the energy which is receiving. Now you see there is an equatorial region and there is a polar region. So in the polar region, of course, the sun's direct radiation generally falls over the tropical region, which is close to the equator, 23.5 to 23.5 degrees north to 23.5 degrees south. There you will receive maximum direct solar radiation. So smaller wavelengths are more available as compared to the larger wavelength. Of course, the larger wavelengths are also available at different times, but in this region, particularly if you average out this 23.5 to 23.5, you can find out that production of ozone is maximum. Whereas in the poleward region, where sun's slanting rays comes, slanting rays tends to fall, there the longer wavelengths are more existing, and because of that the ozone is generally destroyed. Of course, production may be there, production will be there, because these wavelengths will exist, but most of the wavelength which will exist is lambda greater than 0.242 micrometer, and of course this should be less than, this lambda should be less than 0.4 micrometer, because 0.4 micrometer is the start of the visible wavelength. Fine. So this is how the, so in the Antarctic region we talk about ozone hole kind of thing. Well, in the poleward region or in the Antarctic region or in the Arctic region, you will always find that ozone is mostly getting destroyed. Its amount is always low in the poleward region. But along with that, what happened is that due to the artificial or due to this our usage of the CFCs, the chlorofluorocarbons. So usage of CFCs, the chlorofluorocarbons, this has also depleted the ozone layer. So these CFCs are generally used in the refrigerant as a refrigerant. Okay, so it is not harmful in the troposphere, but as it goes into the stratosphere, it releases chlorine atom, and this chlorine atom does not allow this formation of ozone. Rather it destroys the ozone, and this chlorine atom remains. It destroys the ozone and the chlorine atom remains. Okay, I will write the equation of this CFCs kind of thing. So what happens is that this CFCs with H nu, if it reacts, it gives some molecule plus chlorine. This chlorine atom is very important. This chlorine atom, when it reacts with ozone, so O3 plus, sorry, O3 plus Cl will give you O2 plus ClO. Okay. Now this nascent oxygen, one of the nascent oxygen from the atmosphere, that will react with ClO to give Cl plus O2. See, this chlorine atom is remaining, ozone is getting destroyed. So this chlorine atom is again going to destroy another ozone, and like that way this chlorine atom remains in the atmosphere. And not only that, this chlorine atom remains in the atmosphere and continuously destroys the ozone in the stratosphere, and that's why the ozone depletion or ozone hole in the Antarctica region you have found. But this same ozone is produced in the troposphere also. In the troposphere also it is produced. So same ozone is produced in troposphere. Same ozone is produced in troposphere, which may be harmful, which is toxic for us. So what you can see is that the CFCs, the chlorofluorocarbons, which are not toxic for us, we are using it in 1980s or 90s or maybe 2000s also in the refrigerant, that is harming actually us in the stratosphere by depleting the ozone layer, and the harmful UV radiations are coming and resulting into different skin cancer and different diseases. On the other hand, this ozone, which is helping us, protecting us from the harmful UV radiation, in the troposphere, when it is produced, it becomes toxic. It is a pollutant. So you can imagine what is happening. Fine. The immediate next thing which I will be talking about is about the time scales and spatial scales of different atmospheric phenomena. So as I have already discussed that in the troposphere maximum of this weather phenomena exists, atmospheric phenomena exists in the troposphere only, and so you can see that these are the scales and these are the time, this is the spatial scale and this is the time temporal scale. So this is the spatial scale, so this is the spatial scale and this is the temporal scale. Okay. This is the temporal scale. Now so this particular, you can see this seconds to minutes of this time scale, you have a microscale phenomena, that is small turbulent eddies. How you can find out the small turbulent eddies? Someone have asked a question that what is the how we can find this what is this importance of this microscale or small turbulent eddies. So these small turbulent eddies are generally found in the atmosphere but are not much important, but mostly these all things are very important, like thunderstorm events or land sea breeze. Then you have the hurricane or the tropical storm, mid latitude cyclones, long wave, or you have Rossby waves. So turbulent eddies are more important in case of the oceans. And not only that, if you I'm giving you an example of these eddies which you can see, which you can feel, is that you have seen incense sticks. When you fire out these incense sticks, what happens is that you can find out some vapors releasing. So these vapors are generally turbulent eddies, some small micro eddies. Okay, like this, some eddies are there generated. And another is the Rossby waves, the planetary waves. These long waves are nothing but the Rossby waves. These Rossby waves are, what happens is that, see, this is your globe, and generally these Rossby waves are nothing but the jet streams. These jet streams are found circumferring this earth like this way, meandering shape, travels from generally west to east. So see this meandering shape. I know that the polar region is cooler as compared to the equatorial region. So what it is happening is that These regions are cold, these regions are hot. So if you see this particular kind of a meandering, so you can see these winds are bringing the cooler air from the poles towards the equator, and it is taking the equatorial warm air towards the poles. So what it is actually doing is that it is balancing the heat. Higher heat from the equator is going towards the poles, and lower heat from the poles is coming to the region. So what is happening is that the temperature balance of the earth is taking place. Otherwise the equator will be very warm and the poles will be very cold. So this is the importance of the Rossby waves in the atmosphere. Okay, so now you can see that minutes to hours you have thunderstorm development. You can see that thunderstorms, those who are in the northern parts or eastern parts of India, they generally find out in the winter there are several thunderstorms, and particularly the early summer, the pre-monsoon season, there is a possibility of thunder development and storms can be seen, but it lasts for only half to 1 hour. So minutes to hours is the scale of these thunder shower events, and it is a mesoscale event. And this mesoscale events is not 20 kilometer, but it ranges from 10 kilometer. Okay, it ranges from 10 kilometer to some 1000 kilometers. More than 1000 kilometer, if you go to 10,000 kilometer scale, this is nothing but the synoptic scale. Synoptic scale, it's a bird's eye view kind of. So synoptic scale represents these hurricanes and tropical cyclones, which you see the Amphan cyclone and different cyclones every year it comes. Then the mid-latitude cyclones are also present. These are called the extratropical cyclones. So these extratropical cyclones are also in the synoptic scale, because if you have seen ever the satellite picture of the tropical cyclone, it covers the entire Bay of Bengal, and it moves for over a week. It remains for over a week, and it goes towards the Indian landmass. So its movement is of quite a higher scale, and you can see that it goes for days to weeks or more. Fine. Now another thing is that the long waves. These long waves are nothing but the Rossby waves. These long waves are nothing but the Rossby waves, which I have already told you its importance. What is the importance? It helps in balancing the heat. So these long waves are planetary waves. Its scale is more than 10,000 kilometers. So there is a question, I think, in the week 2 which deals with this particular thing. Okay, fine. The next thing is the atmospheric window. Now what happens is that in the atmosphere there are several gases. For example, you have nitrogen, you have oxygen, you have ozone, you have carbon dioxide, you have water vapor, and so on. So on. There are many gases present. And each gases absorbs certain wavelength band of the EM spectrum. Certain wavelength band of the EM spectrum it absorbs. So ozone absorbs like UV radiation, oxygen absorbs some short wave radiation. Okay, then CO2 and water vapor absorbs infrared radiation, right? So all gases generally absorbs, but there are certain wavelength band. Atmospheric window represents those wavelength band in which no atmospheric gases has its influence. Some wavelength bands where atmospheric gases or some wavelength bands which the atmospheric gases do not absorb. So these wavelength bands are helpful for some studies, like satellite data are captured using these wavelength bands. So you can see that this is the transmission. The second figure, if you see, the first figure is the EM spectrum of the sun and the earth over here, and this is the transmission that so you can see that this visible region, say 0.4 to 0.7, is free. So here we can send some signal and get some particular observation, because no signal is being absorbed here. And you can see this 10 to 12 micrometer, which is very it remains in the infrared region, and it is very important for SST measurement by satellite. So this is the concept of the atmospheric window. I will just try to touch this topic, which is important. Those who are working in remote sensing will be getting this particular term uh, maximum times. Okay. The next thing is the atmospheric variable conventions. Okay, so atmospheric variable conventions are like this. For example, you have in which direction you should consider to be positive. So there are many vectors. For example, you have u wind, v wind, w wind. There are many vectors, right? So uh, first of all, let me tell you what is that. What is the meaning of zonal direction, meridional direction, and vertical direction? Okay, so here this zonal direction. So there are three directions mostly in the arts system and sciences. One is the zonal direction, another is the meridional direction, another is the vertical direction. Vertical direction. Now, in which these conventions are that in the zonal direction is nothing but the east-west. East-west direction is the zonal direction. Meridional direction is north-south. Vertical direction is upward and downward. Okay. Generally, this zonal direction is represented by x, meridional direction is represented by y, and vertical upward direction is represented by z. So it will be, its unit vector will be I cap, its unit vector will be j cap, its unit vector will be k cap. Now question is that which is the positive I cap, which is the negative I cap? So let's draw a figure first. For the horizontal thing only I am drawing now, then I will tell about the vertical. So this is the north, this is south, this is east, this is west. Okay, so actually this is your plus I cap, this is your minus I cap. This is your plus j cap, this is your minus j cap. Fine. So what does it implies? That south to north is your positive y or plus j cap. North to south will be negative y and negative j cap. Similarly, west to east is plus x or plus I cap, and then east to west will be minus I cap. Fine. Now this is for the horizontal. For the vertical, let me draw the earth. Okay, this is your equator, this is the center of the earth, and this is the vertical direction. This is positive k cap, this is negative k cap. Okay, vertically upward from the surface of the earth. So upward direction is positive, it is right, upward direction is positive, plus z or plus k cap. Right, this is the convention which is used in the atmosphere. Fine. Now this wind vector v has three components. One is the zonal component, one is the meridional component, another is the vertical component. U, V, W. U represents the zonal velocity, that is the east-west velocity. As I've already told you that zonal direction is east-west direction, is the zonal velocity is the east-west velocity. This is meridional velocity. Meridional velocity means north-south velocity. And this is the vertical velocity, which you can understand easily that upward velocity is positive, downward velocity is negative. So this is the vertical velocity, u, v and w. Now what is the direction here? If you try to draw it in on the earth, well, then the direction will become, this is the equator. So of course this is the direction of k cap, this is the direction of j cap, because the north is here, south is here. So this is the direction of j cap, and the k cap is in this direction, and this x or I cap is going inside the board. So the east is going inside the board, the west is outside the board. So therefore I have written it with a cross. means it is going inside the board. So this is your I cap. Positive I cap will be going inside the board. So this is the convention. So I can write any velocity of the earth as a vector as u I cap plus v j cap plus w k cap. Fine. This is the atmospheric variable conventions, clearly written. Fine. We will use these conventions in the numericals to understand the concepts properly. Okay. The next thing is the PG force, the pressure gradient force. As you have already seen in the week 2, it has been discussed that forces are of two kinds. One is your surface force and body force. You all know this. Forces to surface, and you have body force. Body force like gravity, surface force like friction or viscosity. Okay. And forces are two kinds also in coordinate frame. There is a real force and pseudo force. Pseudo force takes place in the non-inertial or accelerating frame. Whereas the real forces can act in both inertial as well as non-inertial frames. In both the frame, it can act. Okay. Sometimes these pseudo forces are also called as the inertial forces. Although it is acting in the non-inertial frame of reference, it is also called the inertial forces. Remember, the pseudo forces like Coriolis and centrifugal forces, they generally are considered to be the inertial forces. Now this PG force, the pressure gradient force, is nothing but a real force. So since it is a real force, it exists in both the accelerating frame of reference as well as the non-accelerating frame of reference. Earth being a non-inertial frame of reference or accelerating frame of reference, this PG force acts there because it is a real force. Okay. Now I will derive the pressure gradient force, although it is being derived in the lecture. So I will try to derive. So those who have not understood, you can see this particular derivation. And after this, gravity we all know, so I will not waste too much time on gravity. And then the assignment question I will discuss. And after that, some two numericals are also there, which I have framed based on the pressure variation with altitude. That we will do, and after that we will stop the session. Fine. Now comes is the PG force. Well, for this pressure gradient force, we will take a cuboid kind of situation. Let me draw it first. So this is a cuboid. Okay. And this, let us consider that this is your x, this is your y, and this is your z. So x, y, z should be such that x cap cross y cap should be equal to the z cap. I cap cross j cap should be equal to k cap, in this thumb rule kind of a thing. Okay. Now what I will do is that this is delta x in total. Okay, this is delta y and this is delta z, the dimensions of the cuboid. So delta z. Okay. Now at the center, let the pressure be P naught, and there are two walls, as you can see. Let me change the color. So this is wall A. Let me focus only on the x direction first. So this is wall A and this is wall B. Now the forces which will be acting on these walls A and B will be from the outside. So you can see that the force on wall A, Fa, and force on wall B, Fb, are acting in the opposite direction. Okay, so there is a cuboid. From outside the forces are acting, and we will find out what will be the pressure on the surfaces. So first let us find out what is the pressure on the surface A. So PA will be, I will use the Taylor series expansion and neglecting higher order terms. So it will be P naught plus delta P delta x into delta x by 2, right? Because P naught is at the center, so this is delta x by 2, this is also delta x by 2. Fine, this is the PA. And what about PB? PB will be equal to P naught minus delta P delta x into delta x by 2, right? I have neglected the higher order terms. Now what about the force at A? That is pressure at A into area. So it will be P naught plus delta P delta x into delta x by 2 into the area. The area is what? Of A, delta y into delta z, right? Similarly, FB will be equal to P naught minus delta P delta x into delta x by 2 delta y delta z. Same. Area is remaining the same. Fine. And we have also seen with the diagram in blue that FA is actually minus of FB. Therefore, the net force in the x direction will be what? FA minus FB. Minus the direction is opposite, right? So FA is acting in the opposite direction of FB. So now what if I write? Now how will we write this? FA plus FB, right? This is how we will write. Now see, FA is in the negative x direction, so I will give a negative sign. FA is in the negative direction, so I will give a negative sign. So P naught delta y delta z minus delta P delta x by 2 delta y delta z. Fine. And FB is in the positive x direction, so it will be P naught delta y delta z minus delta P delta x by 2 delta y delta z. And I can chop out this particular term. So what I am being left behind with is, if x in the x direction, this will be equal to minus delta P delta x into delta x delta y delta z. Fine. Now just continuing the pressure gradient force, after that I will come to gravity. So now after this what happens is that so what we have seen is the pressure gradient Pg in the x direction is given by minus delta P delta x into delta x delta y delta z on this particular air parcel. Now if we write Fx, or that is equal to Pgx by the mass, if the density of that particular column is, say, rho, of this particular box is rho, then we can write it as minus 1 by rho delta x delta y delta z. That becomes density into volume, that is mass, into delta P delta x into delta x delta y delta z. So what am I writing here is the pressure gradient acceleration. So minus 1 by rho delta P delta x is the pressure gradient Fx, the pressure gradient acceleration. Pressure gradient acceleration in the x. Similarly, in the y direction, the Fy will be equal to minus 1 by rho. Same way, delta P delta y. In the z direction, it is Fz is equal to minus 1 by rho delta P delta z. And if you write it in total, the pressure gradient acceleration will be equal to minus 1 by rho. If you take common, this becomes minus delta P delta x I cap minus delta, minus I have already taken, so delta P delta y j cap plus delta P delta z k cap, and that is nothing but minus 1 by rho grad P. Correct? Okay, now comes is the gravity. We all know what is gravity. So Newton's law of gravitation tells that it is the force between two masses is proportional to the product of the masses, and it is inversely proportional to the square of the distance between the two masses. So F will be equal to G m1 m2 by r square, where G is the this gravitational constant whose value is 6.67 into 10 to the power minus 11 Newton meter square per kg square. And in that only in case of earth, take one of the mass at the surface. So m is equal to, so m2 will be at the surface, will be 1, say, unit mass, and so therefore this gravitational acceleration becomes g m of the earth divided by r square, the radius is square. Of course, from the surface, if you go up, the gravity value will decrease. So this is the gravity, and we know that gravity is acting only in the z direction. So if we consider the momentum equation for non-rotating earth, not the rotating earth, non-rotating earth, we can therefore write that dv dt. So let us write for non-rotating earth, dv dt will be equal to so only real forces will exist because it's a non-rotating earth. So it will be minus 1 by rho grad p, one of the real forces, plus the gravity, which is nothing but in the k cap direction. Another term comes is the frictional force. This frictional force I will discuss in the next problem solving session. The viscosity kind of concepts will be applied there. So this is the momentum equation. In the atmospheric science, this momentum equation is well used for modeling purpose as well as for understanding different phenomena, weather phenomena as well. So this is very important, but this is for the non-rotating earth. That is not the ideal case, that is not the actual case. The actual case is the rotating earth, where you can find out the Coriolis force as well as the centrifugal force as well. Okay, so this is nothing but the momentum equation or the acceleration. You can write it like this. Okay, next is the assignments. So let me go to the assignment section. So this is a week 1 assignment. So as you can see that the numerical value of the solar constant is, we have seen that we have calculated in the lecture 1 that what is the solar constant, what is the value of the solar constant, but here I think the value is same in all the 3 options. But the most important thing which is being checked here is whether you write the SI unit properly or not. So watts per meter square is the SI unit of the solar constant, because it is energy per unit time per unit area. So watts per meter square should be the proper answer. So 1370 watts per meter square is the numerical value of the solar constant. Which region of the solar spectrum is mostly absorbed by the greenhouse gases? Well, infrared region, infrared radiation, because as you know that those greenhouse gases will generally have some peculiar amount of dipole moment, and because this dipole moment has a kind of a vibration which will absorb this infrared radiation. This is the actual concept behind why the greenhouse gases generally absorb the infrared radiation, but because of which the heating of the earth is taking place. So the solar spectrum is mostly the thing which is absorbed by the greenhouse gases is the that infrared radiation. Okay. The next thing is that the rotational period of the sun about its own axis is 25 days at the equator and 35 days at the poles, less at the equator and more at the poles. More time is required for rotation at the poles, and this is called the differential rotation. Well, there is a confusion. Some people have asked this thing, the 24.1 and 29.1 days, but you see which is more nearer. So in week 1 it is presented that it is 24.1 and 29.1. In week 2 it is presented that it is 25 days and 35 days. But you see that it is just to show that 25 days at the smaller number of days at the equator and larger number of days at the poles. So you can use this particular thing. Okay. Now the surface of the sun is known as the photosphere, which we have discussed. It's a factual question. Question number 5 is to solve something. So it has been given that at the surface of the sun, the acceleration due to gravity is 28 times the acceleration due to the gravity on the earth, and radius of the sun is approximately 109 times the earth's radius. So two things which are being given and two things are required only. So what we have to find out is the ratio of the escape velocity of the at the surface of the sun to the surface of the earth. So let's do this particular thing. Okay, so it's given that it is given that the gravity of the sun, the acceleration due to gravity of the sun is 28 times the acceleration of the gravity of the earth. Okay, the E symbol is representing the earth and the S symbol is representing the surface of the sun. And also it is given that the radius of the sun is about 109 times the radius of the earth. Fine, these two informations are given and it has been told to find, oh sorry, keep the annotations, just a minute. Yeah, so now what we have to find out is V at sun divided by V of earth, the escape velocity. These are all escape velocity, and we have already seen the escape velocity formula is nothing but root g to gr. We have also calculated what is the escape velocity of the earth. Okay, so now I will use this formula. So it will be 2 gs into rs divided by root over 2 ge into re, right? So vs by ve will be equal to root of 2 into 28 times the g of earth into 109 times the radius of the earth, and that in the denominator it will be 2 root 2 ge into re. So you chop out this root 2, this root ge and re, root 2 root ge and re. So what you left behind is root over 28 into 109, and if you solve it, it comes out to be about 55.2 is the ratio between the escape velocity of the surface of the sun to escape velocity of the earth, right? Okay, so the answer is 55, which is close. Okay, now in which part of the electromagnetic spectrum sun emits its most of the radiation? Of course, visible. 99% of the radiation of the sun is emitted in the visible range, and we have seen based on this particular concept only we have found out what is the temperature of the photosphere of the sun. The temperature of the core of the sun is approximately, core of the sun is 15 million Kelvin, which is again a fact based question. The primordial atmosphere of the earth had mainly hydrogen and helium. See, any atmosphere initially at a very beginning, since it has come from the sun's composition and earth's composition and different planets composition initially, in the primordial case, it is always the same. Maximum is hydrogen and helium. Then what happens is that with time progresses, this hydrogen and helium is a low density gas, it goes to the space and all other composition remain, and from there this secondary atmosphere tends to form. In the beginning of the earth's atmospheric evolution, the main source of free oxygen was, see, volcanoes always have given the water vapor into the atmosphere, not the free oxygen. Photodissociation has given free oxygen, photosynthesis has given free oxygen. So volcanoes is not the correct option, definitely. What about photodissociation? Well, yes, photodissociation will be the correct option because no organisms were there in the initial stage. So photodissociation is the only process through which the free oxygen has come. Fine. Okay. Next is the blue-green color of the Uranus, again a factual question. This is due to the crystals of the methane. If you read it properly or you see the lectures, you see the lecture notes, you will find out that this blue-green color of the Uranus is because of the crystals of the methane. Jovian planets do not have the solid surface. They do not have these Jovian planets like Jupiter, Saturn. They do not have these solid surfaces. They have some, means rocky surfaces are not present. That's all. Okay, the atmosphere of the Jupiter mainly contains the gas which is primarily is hydrogen. So again, this is a fact-based question. So nothing much to solve here. Okay, so now I go to the second assignment. Okay, so second assignment is this. Greenhouse effect on the earth is mainly due to the carbon dioxide and water vapor. Sulfur dioxide is not a greenhouse gas. Carbon monoxide is also not a greenhouse gas. So carbon dioxide and water vapor is the correct option. Which of the following is not a greenhouse gas? Well, methane is a greenhouse gas. Carbon dioxide we have listed in the week 1. So carbon dioxide is also a greenhouse gas. Well, nitrogen dioxide is not a greenhouse gas, but ozone is a greenhouse gas. We have listed all the gases which are greenhouse gases. And well, NO2 is not a greenhouse gas for sure. N2O is a greenhouse gas, but NO2 is not a greenhouse gas. Nitrous oxide is a greenhouse gas, remember. Pressure and the density of the Earth's atmosphere, today only we have seen that it decreases exponentially with altitude. Okay. Temperature in the mesosphere decreases with altitude. We have seen the zigzag manner curve in the first lecture. So using that you might have solved it properly. So it decreases with altitude in the mesosphere. Okay. Now the temperature in the stratosphere increase mainly due to absorption of shortwave radiation, because I have today also shown, and in the previous lecture also I have shown about the ozone. Ozone absorbs the shortwave UV radiation, and because of which the temperature of the stratosphere goes up. Coldest region of the Earth's atmosphere is mesosphere. The actual answer should be mesopause, because at there only the minimum temperature in the Earth's atmosphere can be found, since it is given as the coldest region. So the actual option should be mesopause, which is not given here. So the nearest option should be mesosphere. Peak electron density in the F region of the ionosphere is about 10 to the power 12 meter cube. So this ionosphere thing I will discuss one day in details. We will see this particular thing. Another is based on the albedo. Albedo is the amount of solar radiation reflected from a particular surface. So if you see the ice or snow, particularly in the polar region, if you see the Antarctic region, there are some ice as well as the oceans. You can definitely see that the oceans has less reflectivity as compared to the ice. Ice is much more brighter as compared to that of the oceans. So oceans have very little brightness or very little albedo as compared to the land. So 4 is less as compared to the 2, that is land. Then comes the cloud. Even you see the cloudy days, you cannot see the sun, you feel very dim light in the lower atmosphere just below the clouds. So you can imagine how much amount of energy it has reflected back. So clouds also have a high albedo, but the maximum albedo is for the ice. So it is 3 greater than 1, greater than 2, greater than 4. Another is that in which region of the electromagnetic radiation Earth radiates its energy? Well, long waves, because you know that Earth, we have already calculated that. Earth's temperature, surface temperature is about 288 Kelvin, that is global average temperature, and we have seen that using Wien's displacement law, we have seen that lambda max, the maximum wavelength due to this 288 Kelvin comes out to be about 10 micrometer, which falls in the infrared region, and infrared region is nothing but the long waves. Which of the following meteorological scale is used to measure the wavelength of Rossby waves? Not the synoptic scale, it should be the planetary scale. I have today discussed it, the planetary scale. Synoptic scale meteorology is used to measure the horizontal lengths of the order. I have today again discussed, it is 1000 to 10,000 kilometers. Fine. And which of the following is not a real force? See, electromagnetic force is a real force, which is used in physics mostly. Frictional force is a real force. Pressure gradient force is a real force. Coriolis force is the only force which acts only in the non-inertial frame of reference or accelerating frame of reference. All other force acts in both the frames. So Coriolis force is the correct option, which is not a real force, it's a pseudo force. Fine. Okay. Now, now these assignments 1 and 2 are being discussed. Now I will do 2 numericals. One is this particular this particular numerical, and another I also have framed based on the second concept of the variation of pressure with altitude. So these 2 numericals I will do, and I will stop the session for today. Okay, fine. So the question tells that In an isothermal atmosphere with surface temperature 288 Kelvin, so assume the dry atmosphere, what will be the pressure at 2 kilometer from the surface? It's not is but if will be the thing. This will be if the surface pressure is 1000 hectopascals. What is given to me? It is given to me that T is equal to, that is 288 Kelvin, and it is an isothermal atmosphere, so that will be nothing but equal to T naught. T naught is the surface temperature. Fine, not required, you just write T is equal to 288 Kelvin. Given it is a dry atmosphere, so okay, fine. Now right now let us not focus on the dry atmosphere. We have to calculate at Z is equal to 2000 meter. Remember this conversion unit, 2 kilometer to 2000 meter, because everything is in the SI units. Okay, and the surface pressure P naught is 1000 hectopascals. I will not convert into pascals because of a particular reason. Okay, so the formula which is used is P is equal to P naught e to the power minus Z by H. Why? Because as we have found out that this pressure variation with altitude in the isothermal atmosphere goes like this: P is equal to P naught e to the power minus Z by H. Okay, where H is the scale height given by R T by G, where all things are constant because it's an isothermal atmosphere. Now this R which is given is the specific gas constant, right? This R which is given is a specific gas constant, and since it is assumed to be a dry atmosphere, so this R will be nothing but RD. And what is the value of RD? We have calculated, it is 287 joules per Kelvin per kg, right? So this scale height H will be equal to 287 into 288 Kelvin divided by 9.81. Fine, we have calculated the H. Z is given to be 2000 meters. P naught is known to me. I will not convert this P naught's unit from hectopascals to pascals because it is in the ratio. So hectopascals will remain, it does not matter. So ultimately we need pressure in hectopascals only. So what happens is that P is equal to 1000 into exponential of minus 2000 meters divided by this H which we have calculated. So let us write it again. P is equal to 1000 into e to the power minus 2000 into 9.81 divided by 287 into 288. Now if you solve this P will be equal to about 1000. Just try to solve it when you are free. Exponential of minus 0.237, and this comes out to be about 788.69 hectopascals. So you can see that from the surface, if you go up to a height of 2 kilometers, the pressure decreases from 1000 hectopascals to 788.69 hectopascals. Fine. So this is the solution. Okay. Fine. The next thing is that the same thing, only in a more realistic situation. So you have to apply those this particular formulation. You have to apply this particular formulation for solving all the assignments, because as you can see in the next question, the lapse rate will not be given. So that is intuitively saying that you have to use the isothermal atmosphere condition, and you have to use this formula for solving the questions in the assignment 3. And we will discuss in details these assignment 3 questions in the next problem solving session. Now, next question is that if an atmosphere whose temperature decreases linearly with height at rate of 6.5 degrees Celsius per kilometer and surface temperature is again 288 Kelvin, what will be the pressure at 2 km from the surface if the surface pressure is 1000 hectopascals? Again, you assume that it is a dry air. Fine. So you assume that it is a dry air. Assume dry atmosphere. What does this mean? The dry atmosphere? It means that the specific gas constant will be equal to RD, which will be equal to 287 joules per Kelvin per kg. That's all. That is the meaning of the dry atmosphere. That is the assumption of the dry atmosphere. And the formulation becomes this: T is equal to 288 minus 6.5 degrees Celsius per kilometer. This is in Kelvin. This is degrees Celsius per kilometer. This is the change. Okay, this is the lapse rate. This is the change. So change can be written as degrees Celsius or Kelvin. It does not matter. So I can change degrees Celsius to Kelvin because it is dt dz. Fine. Into z is given to be 2 kilometers. So I am writing it 2 kilometers so that this kilometer cancels. So ultimately we get 288 minus 2 into 6.5, and that comes out to be 288 minus 13, that comes out to be 275 Kelvin, right? Fine. So we have found out the temperature at, this is the temperature at 2 kilometer height. Temperature at 2 kilometer height I have found out. Or what do we say? The T0 minus gamma Z I have found out. What is T0? Given 288 Kelvin. Right? So this is now done. Now what is the pressure in this kind of an atmosphere? The pressure is P is equal to P0 into T0 minus gamma Z divided by T0 to the power G upon R gamma. Fine. We have calculated this. We know this. P0 is 1000. Given P0 is 1000 hectopascals. I will again not convert these hectopascals to pascals because P and P0 are in ratio. So whatever the P0's unit will be the P's unit. Now next thing is required is to calculate this G upon R gamma. Carefully look at how I am calculating G upon R gamma. So G will be equal to 9.81 meter per second square. R will be nothing but RD 287. But see gamma is not in SI unit, it is in degrees Celsius per kilometer. So I will write 6.5, just from kilometer to meter I have to convert. That's why I have to write 10 to the power minus 3 such that it is in the meter. So now 9.81 into 10 to the power minus 3, I am taking it upward. So it will be 1000 divided by 287 into 6.5. So this will come out to be near 5.25. Okay, so therefore P will be equal to then what? 1000 times T0 minus gamma Z is what? 275. T0 is what? 288 divided to the power 5.25, and if you calculate out this, its answer will come out to be about 784.66 HPA, the hectopascals. Fine. So what we have seen, same thing, only this lapse rate inclusion is there. Same thing, that 288 kilometer is your surface pressure, 288 kilometer is 288 Kelvin is your surface temperature, and surface pressure is P0 is equal to 1000 at 2 kilometer height. If you assume it to be an isothermal atmosphere, it comes out to be 788 near, and if you consider is a realistic atmosphere, it's much less, 784 hectopascals. Okay. So this is the another numerical approach, but again I am repeating, you do not have to use this particular approach, you only have to use this particular formula. And also I will tell you about something like Coriolis force, like just the small formula about the Coriolis force. It says that this suppose you have a disk, okay, rotating disk, because this centrifugal and Coriolis force generally takes place in a non-inertial frame of reference. Since disk is rotating, it's a non-inertial frame. Now if you keep a body just fixed, no motion is there, there will be a centrifugal force, and this centrifugal force is nothing but mr omega square, okay, equal to the magnitude of the centripetal force. Now the same thing, if the object starts moving with some velocity v, then there will be another force which is known as the Coriolis force. Now this is rotating with say some omega, or write it like this, omega. So Coriolis force will be nothing but minus 2 omega cross v. So this is the omega direction, and v is in this direction, so omega cross v. So this angle is theta, suppose, or whatever it is. So you can write it like this. So this is the F Coriolis force. In Earth's case, it will be generally minus 2 omega v sine theta. Okay, 2 omega v sine theta. And omega for Earth's case is about 7.29 into 10 to the power minus 5 radians per second. So using this value and the angle, you can easily find out that this theta is nothing but the latitude angle. So you can find out what is the value of the Coriolis acceleration. These are all accelerations. You have to multiply by mass to get the actual force. So this is the insight of the Coriolis force and centrifugal force in a brief introduction. Just the formula I have given. Using this, you can solve certain assignment questions. Fine. Okay. So that is what I have to show today. And fine. Let me stop here, therefore. Okay, this is done. Okay, so you will get the slides as well as the YouTube link of that particular video recording. And so let me stop presenting.